Hi everyone. Today in this session we are starting a new chapter called Resonant Circuit. Say these resonant circuits are nothing but it is the analysis of AC circuits. Say resonant is nothing but a resonant is a phenomenon. Resonant is a phenomenon and it is a study of AC circuit with resistor, inductor and capacitor are connected in series across AC supply of variable frequency. Let me repeat once again. Resonant circuits. Resonant is a phenomenon and it is a study of AC circuit. That AC circuit consists resistor, inductor, capacitor are connected in series or parallel across a AC supply of variable frequency. Generally, what is the frequency of AC supply in India? 50 Hertz. Say this condition can be obtained, this resonant condition can be obtained by varying the frequency by keeping resistor, inductor, capacitor constant or by keeping frequency as a constant and by varying frequency dependent electrical elements. What are the frequency dependent electrical elements? Inductor and capacitor. There are two ways to obtain a resonant condition. One is by keeping L and C values constant and varying the frequency, or else by keeping frequency constant and by varying the values of inductor and capacitor, because inductor and capacitors are frequency dependent electrical elements. Is it clear? See, in any AC circuit, for example, in series RLC circuit, at resonant condition the current is maximum. In series RLC circuit at resonant condition the current is maximum. The frequency at which resonance occurs, is known as resonant frequency. That condition is known as resonant condition. Is that clear? Here there are two different types of circuits. One is series resonant circuit, second one is parallel resonant circuit. First one is series circuits, series resonant circuit. Second one parallel resonant circuit. See, what is series resonant circuit? When R, L, C are connected in series, let me write this circuit diagram. R, this is inductor and capacitor. All the three elements are connected in series across variable supply. Is it clear? This is nothing but AC supply with a variable frequency. So the resistance is denoted by R and inductor is denoted by L and capacitor is denoted by C. Is it clear? So because when all the three elements are connected in series across this supply, the response is nothing but current, that is AC current. Let me represent it by I. Is it clear? Because the current through all the elements same because all are connected in series. So in any series circuit the current through all the elements same. Next the voltage across the resistor is denoted by VR. What is VR? Voltage across resistor. Next voltage across inductor is denoted by VL. Next, last one, voltage across capacitor is denoted by VC. Is that clear? See, I am trying to explain what is series, what is resonance. Particularly, I am taking series RLC circuit in order to explain resonant circuit. Say R, L, C series circuit, connected across AC supply of variable frequency. Let me discuss later what is that variable frequency, how it affects. Is that clear? Say next, the current through this series RLC circuit depends on impedance of this circuit. The current through RLC series circuit depends on impedance of the circuit, because you know by Ohm's law I is equal to V divided by R. Is that clear? That is for DC circuit. In AC circuit, instead of resistance, we are using impedance. Therefore, I is equal to V by Z. Obviously, when impedance increases, current decreases. When impedance decreases, current increases, because current inversely proportional to impedance. This voltage is nothing but AC supply. Is it clear? Where Z is equal to, so you know what is the general formula to find out impedance of the circuit? Z is equal to R plus J into XL minus XC. This is resistance of the circuit, this is the resistive part, and the second part is known as reactive part. What are the reactive elements here? Inductive reactance, capacitive reactance. What is the general formula to find out impedance? Z is equal to R plus J into XL minus XC. But what is XL? XL is equal to 2 pi FL. What is XL? XL is nothing but inductive reactance, that is equal to 2 pi FL. See, by seeing this equation, the inductive reactance is directly proportional to frequency. Is it clear? The inductive reactance XL is directly proportional to frequency. Therefore, when frequency of supply increases, inductive reactance also increases, because these two are directly related, directly proportional. XL is directly proportional to frequency. Then what is XC? XC is equal to 1 divided by 2 pi FC. What is XC? Capacitive reactance is equal to 1 divided by 2 pi FC. Therefore, capacitive reactance XC is inversely proportional to frequency. Is that clear? See, what is resonant condition means? The response, what is that response? Is nothing but current should be in phase with applied voltage. Is it clear? Current in phase with applied voltage, or indirectly I can say the phase difference between current and voltage is 0. That happens only in case of pure resistor, because in basic electrical engineering we discussed what happens when AC is applied across pure resistor. When AC is applied across pure resistor, both voltage and current are in phase. Both voltage and current are in phase, means there is no phase difference between voltage and current. When AC is applied across pure inductor, voltage is leading compared to current by an angle exactly 90 degree. When AC is applied across pure capacitor, current is leading, voltage lagging, current is leading by an angle 90 degree. In same way, at resonant condition, the current in phase with voltage means what? This impedance of this circuit behaves like a purely resistive. When this condition we can obtain? When XL is equal to XC, because what is the formula here? Z is equal to R plus J into XL minus XC. When XL is equal to XC, these two terms will get cancelled. XL minus XC becomes 0. 0 into J, 0. Then Z is equal to R. Therefore, when Z is equal to R, then the impedance is lowest value. That is the condition where the value of the impedance is minimum. Obviously, when I is equal to V by Z, Z value is minimum, I value is maximum, that is nothing but maximum current. That maximum current is obtained only at resonant condition in case of series RLC circuit. Is that clear? That's why, see, there are two ways to obtain a resonant condition. One is by varying the frequency by keeping L and C constant. That is easy because every time we no need to remove and place this L and C value. Okay. Another way, that is a difficult way. What is that? By keeping frequency constant and changing L and C. Okay. But what we are discussing, we are keeping inductor and capacitor values constant by changing the frequency. For example, what happens? Let me take, this is XL and this is XC. Okay. Initially, when frequency is 50 Hertz, this is the XL value and this is the XC value for frequency 50 Hertz. When frequency increases to 60 Hertz, because XL is directly proportional to frequency, XC is inversely proportional to frequency. When the frequency increases, XL increases, XC decreases. Again, further increase the frequency, again XL increases, XC decreases. Again increase the frequency, XL increases, XC decreases. At particular value of frequency, both XL and XC are equal. At particular value of frequency, both XL and XC are equal. That is known as resonant condition. The frequency at which this condition, which condition? Resonant condition, the corresponding frequency is known as resonant frequency. Is it clear? Therefore, when XL is equal to XC, when XL is equal to XC, this is the condition for resonance. This is the condition for resonance. Then what about impedance? Z is equal to R plus J into XL minus XC. When XL is equal to XC, this part becomes 0. Then Z is equal to R. So this is the where the condition at which we can obtain a minimum impedance value of series RLC circuit. When Z is equal to R, because any value other than 0, some value is going to add with this part. Correct? Anyhow, this is J. If you take a magnitude, obviously you will get square root of R square plus this reactive part value. That's why this is the lowest value of impedance, the condition at which the resonance, what is Z is equal to R. Therefore, I is equal to V divided by R. Actually, what is I? I is equal to V by Z. But what is Z? Z is equal to R. At that particular condition, what is current? Current is maximum. Hope now it is clear. What is resonance? It's a phenomenon and it's a study of AC circuit that consists R, L, C are connected in series across a supply of variable frequency. Then only we can make equal XL is equal to XC. Is that clear? So by varying the frequency at particular value of frequency, XL becomes equal to XL is equal to XC. Therefore, impedance of this series RLC circuit behaves like a purely resistive. Then Z is equal to R. Then what is I? I is equal to V by Z. When Z is equal to R, I becomes I maximum. Now tell me, what is resonant current? This is the maximum current which is obtained only at resonant frequency. The frequency at which resonance occurs, that frequency is known as resonant frequency. Yes, let me obtain the expression for resonant frequency. What is the condition for resonance? XL is equal to XC. This is at resonance, right? That's why let me represent it XLR, XCR. What is that? R represent at resonant condition. This is the condition at which at resonance, right? That's why XLR is equal to XCR. Resonance is with respect to frequency. Remember, Resonance is obtaining with respect to frequency. When frequency increases, XL increases, XC decreases. Again the frequency increases, XL increases, XC decreases. By only varying the frequency of the supply, XL is made equal to XC. Is it clear? That's why it is frequency related component. That's why XLR is equal to XAR, because there is a frequency component inside XL. What is XL? 2 pi FL. What is XC? 1 divided by 2 pi FC. Is it clear? But these are related to frequency. Now what is XL? 2 pi FL. Again F becomes FR, because resonance is with respect to frequency. That's why 2 pi FRL is equal to what is XC? 1 divided by 2 pi FC. Again this R is with respect to frequency. Is it clear? What is this? 2 pi FRL, that is equal to 1 divided by 2 pi FRC. Now FR into FR square is equal to 1 divided by 2 into 2, 4, pi into pi square L into C. Take a square root. FR is equal to what is square root of 4? 2 pi square becomes pi square root of LC. This is the formula to find out the resonant frequency of any given RLC series circuit. What is that formula? FR is equal to 1 divided by 2 pi square root of LC. What is L? Inductance of given RLC circuit. What is C? Capacitance of given RLC circuit. Is that clear? Now try to understand this sentence. At resonance, the supply current, I mean the response, that is nothing but current, is in phase with voltage. In phase means what? The phase difference is 0. Is it clear? That is obtained only at resonant condition. The supply current in phase with supply voltage at resonant condition. There is no phase difference between current and voltage. Both are in phase. The phase difference is 0. Let me write in order to understand in a clear way. Let me represent phasor diagram. Phasor diagram. See, first, which one is the reference while writing the phasor diagram for RLC series circuit? Current is the reference. Why current is the reference? Because it is a series circuit. The total current through R, current through L, current through C, all are same because it is a series RLC circuit. In any series circuit, let us consider I as a reference. Okay, there is only one current in the circuit, but how many voltages in the circuit? There are 4 voltages. One is voltage across resistor, next voltage across inductor, next voltage across capacitor, and this one is nothing but total supply voltage or applied voltage. Now let me draw one by one. First VR. VR means what? Voltage across resistor. Means voltage across resistor with respect to current. We already discussed in basic electrical engineering. When AC is applied across pure resistor, both voltage and current are in phase. Means if you are discussing with respect to waveform, both are crossing, both voltage and current are crossing the reference, I mean time axis at same interval of time. Is it clear? The phase difference is 0. That's why we are in phase. Means the angle between VR and I is 0. There is no phase difference between voltage across resistor and current through the resistor, because the total current is nothing but current through the resistor. So we finished VR. Then what is VL? Voltage across inductor. See, when AC is applied across pure inductor, voltage is leading with respect to current. Means voltage is leading with respect to current. In case of pure inductor, the voltage leading by an angle exactly 90 degree. See, voltage across inductor is represented by VL, right? This is leading exactly by an angle pi by 2, that is nothing but 90 degree. So, VL is over. Next VC. What is VC? Voltage across capacitor. See, when AC is applied across a capacitor, current is leading. Because the circuit behaves like a capacitive circuit. In capacitive circuit, current leading, voltage lagging by an angle pi by 2. This is VC, this is lagging by an angle pi by 2. Is it clear? Now, what is VL? What is VL? I into XL. What is VC? I into XC. At particular value of frequency, at what is that frequency is known as resonant frequency. XL is equal to XC, right? At resonant frequency, XL is equal to XC. But for both XL and XC, the current is multiplying, that is same current. Why it is same current? Because it is a series circuit. The current through inductor and current through capacitor is same. If same current is multiplying with same values, what happens? Obviously, VL is equal to VC. VL is equal to VC. Both voltage across inductor and voltage across capacitor both are equal, but both are in opposite direction. Both are equal but opposite direction. So these two quantities will get cancelled. Both voltage across inductor and voltage across capacitor both are equal but opposite direction. That's why VL cancels VC. That's why the applied voltage is nothing but voltage across the resistor. Because what is the KVL statement? The algebraic sum of the voltage in any closed loop is equal to 0, or else the applied voltage is equal to algebraic sum of the voltage drop across individual passive elements. Is that clear? So that's why VL is equal to VC. So VC will get cancelled. VR is nothing but total applied voltage that is in phase with current. That's why at resonant condition, any AC RLC series circuit behaves like a purely resistive circuit. That's why both voltage and current are in phase, and obviously the current is maximum, the impedance of the circuit is minimum, that is equal to R. Then what are the salient features of this series RLC resonant circuit? What are the features of this series RLC resonant circuit? Let me list one by one. First one is XL is equal to XC. This is the first one. So this is achieved by varying the frequency, right? At particular value of frequency, XL is equal to XC. What is that? Inductive reactance is exactly equal to capacitive reactance. Therefore, inductive reactance cancels the capacitive reactance. That's why Z is equal to R. That is the first one. Second one, Z is equal to R. What is this Z is equal to R? The impedance of the circuit is nothing but resistance value, because what is XL cancels the XC, therefore the impedance of the circuit behaves like a purely resistive. Is that clear? Next one, third one is I naught or IR are represented as a resonant current. Is it clear? Sorry. Resonant currents are represented by I naught or IR. That is nothing but V by Z. Correct? But what is Z? That is V by R. V by R. So maximum current is nothing but resonant current, that is equal to V by R. Next, power factor. What is power factor? That is also the term we discussed in basic electrical engineering. Power factor is the ratio of resistance of the circuit to the impedance of the circuit. I mean, it is the ratio of resistance by impedance of the circuit. First, let me write cos phi. Power factor is represented by cos phi, that is equal to R by Z. But at resonance, what is Z? Z is equal to R. Therefore, R divided by R, that is equal to 1. Then what is the fourth salient feature of series RLC resonant circuit? The power factor is unity. Power factor is unity. And the last one, fifth one is equal to VL is equal to minus VC, or directly we can write VL is equal to VC. The voltage across inductor and capacitor are equal but opposite. What is the last point? The voltage across the inductor and capacitors are equal and opposite. Is it clear? These are the salient features of series RLC circuit. Okay. Now, let us discuss the next topic, variation of current with respect to frequency in case of series RLC circuit. So, what is the topic? Variation of current I with respect to frequency. See, all the frequencies are not resonant frequency. Is it clear? The frequency at which resonant condition occurs, that frequency is known as resonant frequency. Now, we can draw, say, let me represent x-axis as a frequency and y-axis as current. Is that clear? Now, see, the first I will draw the curve, later I can explain this. See, this is how the variation of current with respect to frequency, right? See, initially, let me represent at this particular frequency, the current is maximum, right? Then what is that frequency? Resonant frequency. At resonant frequency, the current is maximum. At resonant frequency, the current is maximum. This is the maximum current. And let me mark two band frequency. So, this one is known as F1. F1 is also known as lower cutoff frequency, and this one is known as F2. F2 is known as upper cutoff frequency. At frequency F1 and F2, the current value is same. At both F1 and F2, the current value is same. That current is nothing but Im by root 2. That is nothing but 0.707 Im. That is also known as effective value. You might have heard RMS value, the effective value of the alternate current, that is same at both the frequency F1 and F2. This is how the curve looks. What is that? The variation of current with respect to frequency. There are three frequency here, I denoted here. One is the F1, lower cutoff frequency, and F2, upper cutoff frequency, and at resonant frequency, the current is maximum. Fine. See, initially, the frequency less than Fr. See, these are the frequencies up to from this point, these are the frequencies are less than Fr. I mean, less than the resonant frequency. What happens? The frequency values are low. It's starting from 0 hertz, 1 hertz, 2 hertz, 3 hertz. For example, Fr is equal to 25 hertz. After this, 30 hertz, 40 hertz, 50 hertz. The frequency less than Fr. In all the frequencies are low frequencies. All the frequencies are low frequencies. At low frequency, which value is high? Because Z is equal to R plus J into XL minus XC. XL is directly proportional to frequency. XC is inversely proportional to frequency. See, at lower frequency values, Because when XL is directly proportional to frequency means the frequency value less than FR means XL value is also low. The frequency value less than FR, that is lower frequency, means XC, this XC is inversely proportional to frequency. At lower frequencies, which value is higher? XC is greater than XL. Correct? So, XC is greater than XL because these are the range of frequencies or low frequencies. At low frequencies, which value is higher? XC is higher compared to XL because XC is inversely proportional to frequency, whereas XL is directly proportional to frequency. When XC is greater than XL in this circuit, when XC is greater than XL, the circuit behaves like a capacitive circuit. Because XC is greater than XL, the circuit behaves like a capacitive circuit. In capacitive circuit, which quantity is leading? Voltage or current? Current is leading with respect to voltage. Therefore, current is leading. Is it clear? The frequencies, next, the frequencies greater than resonant frequency. I mean, after this resonant frequency, see the current value is decreasing. Here, the current is increasing up to the resonant frequency. What is the current value at resonant frequency? Maximum. After this maximum value, what is this? Z impedance of the circuit at resonance, Z is equal to R. At this point, what is the impedance of the circuit? Z is equal to square root of R square plus XC minus XL. Here, XL minus XC. So, at this point, XL is greater than XC, therefore, current lagging. Therefore, the current lagging. See, in both the cases, here, what is the condition? XC is greater than XL. Here, XL is greater than XC. But at particular frequency, F1 and F2, the current is same. What is that? Im by root 2. So, that is why these two frequencies are also known as cutoff frequencies, band frequencies. Is it clear? So, I think you understood this concept. F less than FR, the current XL is greater than XC, therefore current lagging. Because when XL is greater than XC, the circuit behaves like an inductive circuit. In inductive circuit, which parameter is leading? Voltage is leading, current lagging. Is it clear? The range between F1 and F2. The range between F1 and F2 is known as band frequencies. The band frequencies range is known as bandwidth, that is nothing but F2 minus F1. What is bandwidth? The range of the cutoff frequencies, the algebraic difference between upper cutoff frequency and lower cutoff frequency is nothing but bandwidth. Is it clear? These two frequencies are also known as half power frequencies. Please try to understand this sentence. F1 and F2 frequencies, these cutoff frequencies are also known as half power frequencies. Why it is known as half power frequencies means, so whatever the power supplied by the source to the circuit at resonant frequency, compared to that frequency, resonant frequency, the power supplied by the source at F1 and F2 is half of the power supplied by the power supplied to the circuit at resonant frequency. Is it clear? So, let me prove that. Say P max is equal to, P max means what? Maximum power, that is equal to maximum current square into R. Because see, at resonance, Z behaves like a resistance. Impedance of the circuit behaves like a resistance. But at frequency, this is what at F0. F0 is nothing but FR at resonant frequency. Next, at frequency F1 and F2. F1 and F2 are known as cutoff frequencies, right? So let me represent it by P dash. Then what is the power? The general formula to find out the power, I square into R, right? Then what is current at F1 and F2? The current at F1 and F2 same. The current at F1 and F2 is same. What is that? Im by root 2. Therefore, P dash is equal to Im by root 2 whole square into R. Im by root 2 whole square into R. Therefore, P dash is equal to Im square divided by Im square into R divided by 2. Just compare these two. See, this is the power supplied at resonant frequency. What is that? Im square into R. This is the power supplied at cutoff frequencies, Im square R divided by 2. That's why these two frequencies are known as half power frequencies. Is that clear? What is bandwidth? The range between lower cutoff frequency, upper cutoff frequency, or we can say the algebraic difference between upper cutoff frequency and lower cutoff frequencies are known as bandwidth. So F1 and F2 are also known as half power frequencies because the power delivered to the circuit at F1 and F2 is half of the power delivered at the frequency known as resonant frequency. Thank you.